A vector is a quantity in mathematics that has a magnitude, distance, velocity, or size, and a direction, as on a compass needle like west, up, down, or north by northwest. Rowing a boat across an inlet, you may think you are rowing due south at 3 knots, but if the tides are receding, you could be moving at 5 knots southeast. A vector or several vectors working together will take into account the distance you row, your speed, and your actual direction. To represent vectors, mathematicians, physicists, and engineers use rays, labeling them with lowercase or uppercase letters like this. All vectors are named tail, starting point, to arrowhead, which is why we have vector AB and not vector BA. If you are labeling your vectors, the decision to use uppercase or lowercase lettering rests with you. Vectors can be parallel and pointing in the same or opposite directions. Look at the arrowheads. If you are given vectors, pay attention to the direction of the vector. Look at the arrowheads. Vectors of equal magnitude but pointing in opposite directions are opposites, so vector B can also be written as negative A, which negates the magnitude of A. A vector with unit length is called a unit vector and is symbolized by what is known as a hat. To add vectors, we connect the tail of one vector to the head of another using an arrow. The direct line ray connecting the two vectors is the resultant R. We add vector CD to vector EF and get resultant R. Here's a stumper. Does this figure give the same result as the previous figure? Here we add vector EF to vector CD and still get resultant R. Vectors follow the same rules of arithmetic as whole numbers, in this case the commutative property. Now let's look at vector subtraction. Vector subtraction only takes 2 steps. 1. Negate the vector you wish to subtract. 2. Then add the two vectors together. Here are vectors SA and IL, showing the route we thought we were taking on a sailboat. For whatever reason, instead of following vector IL, we went in the opposite direction. So instead of adding vector IL, we need to subtract it. We do that by negating vector IL and adding it to vector SA, which looks like this. SA plus negative IL equals R. Multiplying a vector by a scalar, a real number, is called scalar multiplication. We know that vectors have 2 parts, magnitude and direction. We cannot multiply direction, but we can multiply the vector's magnitude. Multiplying a vector times a positive whole number scalar greater than 1 produces a larger vector. Multiplying a vector times a negative whole number scalar less than negative 1 produces a larger vector in the opposite direction. Multiplying a vector times 1 returns the same vector, 0 displacement. Multiplying a vector times a positive fractional scalar less than 1 produces a smaller vector. Multiplying a vector times a negative fractional scalar greater than negative 1 produces a smaller vector in the opposite direction. The magnitude of a vector is shown as an absolute value, or with 2 lines to avoid confusing it with absolute value. If you know the x-axis and y-axis values of a vector, you can easily calculate its magnitude by applying the Pythagorean theorem to the change in position from tail to arrowhead. So here, with the tail at 1,4 and the arrowhead at 7,8, we have a change in x value of 6 and a change in y value of 4. So, the magnitude of vector u equals the square root of 6 squared plus 4 squared. Then we simplify and solve, and we come up with our answer. The magnitude of the vector is 7.2111 units. The unit is determined by what you are measuring: inches, kilometers, miles per hour, etc. A displacement vector cuts from start to finish in a straight line. In this figure, we can see the displacement vector is also the resultant. The calculation of displacement is still vector n plus vector v equals r, because vectors a and y negate each other. Test what you've learned with the basic vector problems at the bottom of the written lesson below.